Yeah, in today's lecture, we are going to see how these capacitor and inductors are going to behave when you have a DC bias, right? So far, we have seen how the inductor and capacitor behaves under AC bias, and in this class, we are going to see how the capacitor and inductor going to behave when you connect them to a DC voltage. Right? For example, okay, I'll draw a circuit, right? I'll draw a circuit. Well, first consider RC circuits, right? A circuit which has RC circuits, right? A circuit which, oh, sorry. Right, you can see them now. Right? You can see it now. Is it okay? Is it clear to you? Yeah, yeah, you can send me a message in chat, right? Always. If you cannot see it or if my audio is not clear, please always send me a message in group chat, right? So I will change it accordingly, right? So an RC circuit. An RC circuit is nothing but consists a capacitor and a resistor. Okay, consider this circuit, right, which has a resistor R, right, and then this circuit have a capacitor C, right, a capacitor C, and in this side we will connect it to a battery, right, a huge battery with EMF of V, right, like this VCR. But this is a two-way switch, right? This can move like this, right? This is a two-way switch, right? So what we do first is we will connect this one here, right? When we connect the capacitor to the battery, the capacitor will get charged. Am I right? As I said, if there are two parallel plates, so this capacitor will get charged, right? Until the voltage across the capacitor becomes voltage V, right? So you need to connect it for a long time to get that voltage V, right? So just an example, for a certain amount of time, you are connecting it to the battery and then it's being charged. Now the voltage across the capacitor is V, right? After that, now you are just turning the switch to the resistor. Right now, the battery is completely removed from the circuit, and now you have simply like this, right? I can redraw the circuit something like this. You have a capacitor with a voltage of V and a resistor R. Am I right? You have simply have a capacitor with a voltage of V and then have a resistor R. Right now you have a kind of, I would say, yeah, the voltage across this one or the voltage between these 2 points A and B, right? So I can write it as VAV is V. Clear? The voltage across point A and B are V, right? Immediately after removing the circuit, right? Immediately after removing the or immediately after this one, right? I can say that at t equals 0, right? So t naught, right? At t equals 0, I can say that, right? VAV is equal to, okay, let's take it as V naught, right? Which will be easy for us, right? VAV equals V naught, right? Now, right after connecting, the very next moment, a current will start flowing through these two branches, right? A current will start flowing these through branches because we have a voltage difference of V, and then you will have a current through these two branches, right? So I can write it as, let this current through capacitor is IC and the current through resistance is IR, right? So I can write it as IC plus IR equals 0. Right, so what is the current through the capacitor? We have already seen that. So C into dV by dt, right? The current through the capacitor can be written as C into dV by dt plus the current through the resistance become V by R, right? Which is equal to 0. Right, so now I can simply write this as, right, so dV by dt equals minus 1 over RC into V. Am I right? I just bring this on the other side so that which becomes minus, and then C to the denominator, which becomes RC into V. Now, let me cross multiply dt here and V there. So I can write it as dV over V equals minus 1 over RC into dt. Am I right? Right, so what I can do is I can integrate both sides, right? So yeah, RC becomes constant. So dV over V becomes ln V, right? Natural log of V equals 1 over RC into integration T becomes T plus a constant, right? Let me take it as, okay, we'll make it as, right, an integration constant, right? An integration constant. Right, now we need to find out the integration constant. For that, we can apply this condition, right? So at t equals 0, we know that VAB becomes V naught, right? Apply that one here. So ln V naught, right? So at t equals 0, V equals V naught, right? So ln V naught equals 1 over RC into T becomes 0, right? So into 0 plus constant, right? So we can write that the integration constant, right? CONST equals ln V naught, right? The integration constant becomes ln V naught, right? Okay, now substitute that ln V naught there, right? And then bring it to the other side, right? So we can write it as, yeah, so ln V equals minus T by RC, right? Plus ln V naught, right? ln V naught. Now, what we can do is, we can bring this on the other side, right? So ln V naught becomes ln V minus, so we can write it as ln V over V naught equals minus T by RC, right? ln minus, oh sorry, yeah, that is minus, right? So that T becomes 0, right? So constant become V naught. Let's side of the paper can't see. Can you see now? Hello? Yeah, okay, right? So we can write it as ln V over V naught equals T by RC. Right. Now, what we can do is, so I'll rewrite, simply take natural log both sides. Natural log means e to the power, right? E to the power. So we can, if we take e to the power to ln, so we can write it as V by V naught equals e to the power minus T by RC. Am I right? T by RC. Or I can write V equals V naught into e to the power minus T by RC. Right? So this is the voltage V after T seconds. Right? After T seconds. Now you can see that whenever you are connecting a capacitor to a resistor, right, the voltage V or even the current depends on time. Right? Depends on time. Right? And the function is actually V equals V naught into e to the power minus T by RC. Right? If we draw this one in a graph, right? In a graph, right? So that will be something like this, right? Let this be V, right? The voltage, and this is time, right? This is time, and as we know that, right? This is V naught, right? V naught, and immediately starts its e to the power minus T by RC, right? So it will reduce exponentially, right? It will reduce exponentially and will reach zero somewhere in the zero axis, right? So we can name this as, right, e to the power minus T by RC, right? Also we can denote this RC, right? RC, 1 over RC, or the RC as time constant, right? So we can use a notation, right? Tau equals RC, or we can call the tau as time constant, right? Time constant, right? Tau is actually what tau is. Tau means is, right? Let 1 over RC, right? So 1 over RC means, so if it becomes 1 over RC, so this will be about, yeah, so V naught by E. Hope E is 2.71, right? 71. So 1 over E means the time taken at, right? So V naught by E, right? By E actually. E, a natural, right? So this will be your tau. Right, this will be your tau, right? So after RC seconds, right, your V out will be V out over E, right? Because RC means, yes, okay, you can simply substitute, which means after second, and then you can call that as time constant, right? So whenever you have a circuit with a capacitor, as I said earlier, in AC signals, the current through the capacitor depends on the frequency, right? If it is DC, then the current through the capacitor depends on the time, right? Depends on time, right? So this is the transient current through RC circuits, right? Now let's see how it behaves, or how an LC circuit, sorry, an RL circuit, right? So RL circuit is, can you see it clearly, or the writings behind the paper is disturbing you? It's okay, no? Right, okay. Okay, so now we'll do the same thing again, but with an inductor. Right, we'll do the same thing but with an inductor, right? So what I can do is, I can have a resistor and an inductor, right, which is connected to a battery, DC battery, right? DC battery, and this is a two-way switch, right? This is a two-way switch. Let this be V naught, and the inductance is L, and the resistance is R, right? So what I am doing is, first I will contact L to the battery, and I will store the magnetic field in the inductor, right? I will leave until the inductor is fully charged, right? And until the inductor is fully charged. And now what I can do is I will simply going back, right? After it is fully charged, I am fully stored with the magnetic field. I am just connecting this there, right? So what I can do is I can, after connecting it to the resistor, I can redraw the circuit something like this, right? Like a simple RL circuit, right? This is resistance R, this is inductance L, right? Let's leave point 1, right? A and B. Now, it is not the voltage, right? Actually, let's consider the current through the loop. Let's consider the current through the loop, right? O, right? Because it is going to be I. And then we'll mark the voltage across the inductor as VL and the voltage across the resistor as VR. Right? So voltage across the inductor is VL and the voltage across the resistor is VR. Right? So we can simply write it as, okay, by using Kirchhoff's voltage law, right, inside this loop, yeah, these two voltages. So when you add these two voltages, they must be equal, right? So VL plus VR must be equal to 0. And we know what VL is, right? If this current is I, right? If the current is I, we know what VL is, right? So VL, we can write it as L into di by dt, right? L into di by dt. We have seen it on our very first class, right? And VR can be written as R into I, right? R into I, which is equal to 0. Right now, we can write this as, of course, right? So, yeah, this can be written as di by dt equals, right? So, this can be brought to the other side. So, minus R and then L can be bring it here over L into I, right? Minus R over L into I. Right now, okay, cross multiply this time, right? Cross multiply the time. So we can write it as integration, right? So di over I, right? Integration, right? We'll bring this one. So di over I equals minus R over L into integration this dt. Right, 1 into dt, or we can write it as 1 into dt or integration dt, right? Similar to the previous step, what we can do is, yeah, this becomes ln I equals, right, so minus R over L into t plus constant. Am I right? RL over L into T plus a constant, right? A constant, right? The same thing we can do it, right? Let's take at initial rho at T equals 0, I equals I naught, right? At T equals 0, I equals I naught, right? So what we can do is we can find the constant as, right, ln I naught, right, similar to this one. So at t equals 0 seconds, we can write it as ln I naught is equal to, right, so t0 means the whole term will be 0 plus constant, right? So I can substitute this over there, right? So I can rewrite this as ln I equals minus R over L into T plus ln I naught, right? Ln I naught. Now I can bring this on there, ln I naught minus I1, I can write it as ln I over I naught right? So, and then take, okay, I'll write it step by step, right? So, ln I over I naught equals minus R over L into T, right? Just take natural logarithm both sides, right? Just take natural logarithm both sides. So I can write it as I equals I naught into, right, e to the power minus RT by L. Right, so what we had in a capacitor is actually V equals V naught into e to the power minus E by RC. For an inductor, I equals I naught into e to the power minus RT by L. Right, so the transient current I at time t equals t second can be written as I naught into e to the power minus RT over L. Right, so this is the simple equation to calculate the transient current through the inductor. Right, now we'll draw the current versus time graph, right, as we did for capacitor. Right, so this is time t and this is current I, and it starts with I naught. Again, it is e to the power something into minus t, so that will reduce exponentially, right? That will reduce exponentially, right? So here also we can use a time constant tau, right, which is now L over R, right? So we can write this as e to the power minus t over tau, right, where your tau equals, right, L over R, the ratio between the inductance and resistance, which you have used in your circuit, right? So that will be simply L over R, and then again at t equals tau, this will be simply I naught by E, right? This will be your tau, right? So, right, so yeah, E is 2.71 something, right? Right, so let's see how the capacitor and inductor behaves when they are connected to a circuit. Right, let me have a circuit P naught, a capacitor C, and then a resistor R. Right, C, R. Right, so I can apply Kirchhoff's current law, so I can write it as simply, right, so let the voltage across the capacitor is VC and the voltage across the resistance is VR, right? So I can write it as Q equals C into V, am I right? Capacitor Q equals C into V, or I can write VC equals, right, Q by C. Am I right? VC equals QIC. Yeah, what is the difference between small I and capital I? Okay, it's actually to differentiate, right? If you are using in general notations, if you are using DC currents, you will be using capital I, right? If you are using AC current, they will be small letters, right? Small I means that is either depends on time, right? Kind of I of t, right? Which means I is a function of time, or I is an AC signal. Small I naught equals I naught, I equals I naught into sine omega t, right? So if they are mentioned, right, in various books uses various notations, but this is what I use, right? If it is a variable, then I'll use it as a small I. If it is a constant current, I will use capital, right? So we can here, since we are handling with AC signals, sorry, DC signals, we can use this one, right? So I can write it as VC equals Q over C, and simply VR equals I into R, right? So I can write it as, right, I can write it as V naught equals, right? So I can simply write it as, yes, Q by C into plus I R. Right now, differentiate this with respect to time, right? Differentiate the whole equation with respect to time, right? So dt of V naught equals dt of Q by C plus dt of I R. All right, IR. So since V naught is a DC voltage, that's a constant, right? So I can write it as V naught, ddt of V naught becomes 0, right? So, and also 1 over C is a constant, so I can simply write it as 1 over C into dq by dt plus, again, R is a constant, I can write it as R into di by dt. Clear? di by dt. Now what I can simply do is, right, I can bring this other side, so I can simply write it as so dq by dt. What is dq by dt? Becomes I, right? Rate of change of flow of charge is your current, right? So I can write it as I, right? So simply right, so I can write it as minus I over C, right, equals, okay, I over RC equals di by dt, right? Just cross multiply this one, so we can write it as di by I equals dt by RC, right? Di by I, because I am just bringing this one there, dt there, and just changing the equation. Sorry, yeah, I will have, yes, there should be a minus, right? There should be a minus, right? Now, what is I over I? Again, that becomes ln I, right? So ln I equals, right? If you integrate this one dt over RC, that becomes minus T by RC plus constant. Right, again, at T equals 0, the current is I naught, so I can write it as I equals I naught into e to the power minus T by RC. Right, this equation is similar to the equation what we have got for the sorry, yeah, this one, right? T by RC, here you are getting this one, right? So it is similar to that one, but the procedure is same, right? So you can use this one to solve simple problems, right? You can similarly you can calculate the current through the inductor, right? Current through the inductor when it is connected to a DC circuit, right? So yeah, so okay, right, let's see from this circuit we can draw the current, right? When you are connected to a DC voltage, you can draw the current I and time t, right? So it will start from t and it will be reaching 0 at some time, right? It will be reaching 0 at some time. Let's take it as t dash, right? So we can say that if a capacitor is connected to a DC source, right, at initial conditions, which means assume that the capacitor does not have any charge, right? until it is fully charged. There will be a small current, right? When it is fully charged, there will not be any current. It will be completely open circuit. Clear, right? So, a capacitor is connected to a DC voltage. We can consider it as an open circuited one once it is fully charged. Right? Fully charged means if it has all the QC charge in the capacitor, or a Q by C charge in the capacitor. Right? So once the capacitor is fully charged, right, there will not be any current through the capacitor, right, when it is connected to a DC charge, DC voltage source, right? So, okay, we'll see all these things, or we can discuss all these things in our next in our tutorial sessions, right? In our tutorial sessions next class. Okay, shall we try an LC circuit as well, right? So this is a RC circuit. We'll try an LC circuit as well, right? There's nothing different, right? The procedure is same, right? Okay, let's have a voltage V0, an inductor, and a resistor. Right, an inductor and a resistor. Let this be L and R. Right, so this is V0. Similarly, the voltage are equal to V0. Right, so VL, right, let this be VL plus VR is equal to V0. Right, and then we can write VL as L into di by dt. Right, L into di by dt, which we have seen in our very first class, plus I into R, right? VR equals I into R equals V0, right? V0. Now, okay, now what we can do is we can write it as right. So let this be right. Okay. di by dt plus R over L into I equals V0 over L. Am I right? Am I right? So you can simply have a differential equation, right? A differential equation to solve it. Or else, what I can simply do is we can yes, I can bring this on the other side and then okay, we'll approach it in this way, right? So let this be di by dt, right? We can simply use the partial differential equation, or we can go like this, right? I equals V0 over L minus R over L. Am I right? R over L into I. R over L into I. V0 over L. Yes. R over L into I. So simply I can rewrite this as oh no, yeah. Yes, so simply we'll okay, right? It is okay. It's easy, but still, yeah, you need to have. Let me have R over L as common, right? I'll take R over L as common, right? R over L as common, right? So I can rewrite this as, right? So I can rewrite this as V naught over R. Am I right? If you multiply this, R will get cancelled. You will have simply this one, right? So V naught over R minus I, right? Minus I, right? So simply I will bring this one the other side, right? I will bring this one the other side. Okay, I can put another minus also, right? To make it as easy, right? So I can put minus here, minus R over R naught here. So this becomes minus and this becomes plus, right? I will make it further simple, right? We can compare it easily, right? So this, I can rewrite this as, right? So di by, so this becomes I minus V naught by R, right? I minus V naught by R, this plus and this minus, right? So di by I minus V naught by R equals minus R over L into dt, right? Minus R over L into dt. Right, this is again, if you integrate this one, you will have ln 1 over, so I can simply write this as I ln I minus, right, V naught over R, which is equal to, right, this will be minus R T over L plus constant, right, plus constant, right. Similarly, at t equals 0, right, at t equals 0, right, so current I is also equal to 0, right, current I is also equal to 0 at initial, right, at initial when t equals 0, I is also equal to 0. Now substitute those here, right, so I can simply write it as ln minus V naught by R is equal to constant. Am I right? ln minus V naught by R is equal to your constant. Right, now we will substitute this here. Right, so this will be ln I minus V naught by R is equal to minus R T by L, sorry, L plus ln minus V naught by R. Right, bring this one there, so that will go down, or simply we can write it as and take natural logarithm both sides, so I can simply write it as I equals, right, so this V over R becomes 1 over VR, so right, I can write it as, and then V naught R over V naught R becomes 1, minus 1 becomes plus 1, right, which will be equal to V naught over R minus B naught over R into exponential, right? If we multiply this one, we can take it as e to the power minus R T by L. Or simply we can write it as B naught by R into 1 minus e to the power minus T by, I can write it as L over R, am I right? Right, I can bring this R here, right? I can write it as T by L over R, which is equal to your current I, right? So this is your current through an inductor, right? So what is V naught over R? Is actually the current through the capacitor when the inductor is short circuited. Am I right? When the inductor is short circuited. So when t becomes infinity, infinity means when the inductor becomes fully charged, right? When t becomes infinity, what is e to the power minus infinity? e to the power minus infinity is 0, right? E to the power minus infinity is 0, right? So 1 minus 0 becomes 1, right? So at stable, you can say that the voltage across the inductor VL becomes 0, right? So we have seen that the voltage across the inductor is e to the power minus 1 over inductor, yes. So the current is this one, then voltage is actually the inverse. So that's what we use the L over R here, right? So this L over R we are using here for comparison, right? T over L over R, where we have L over R, which is our time constant tau, right? So I can write it as T by tau, right? So if I draw the current through an inductor, right? So it is I and this is T, right? And this becomes V naught over R, right? V naught over R, right? So at initial, the time will be, current will be 0 and it will be increasing exponential, and then will be getting stable at T over R, right? Because when T becomes infinity, minus infinity is 0, right? Any value to the power minus infinity becomes 0. So 1 minus 0 means 1 into V by R. So after the inductor is fully charged, right? So we can say that when you are connected an inductor to a DC, until it's being stored the magnetic field, there will be a change in current, right? Once it is fully stored, then there will not be any voltage across the inductor, or the inductor will act simply as a 0 ohm resistor, right? So this is what it will be working, right? So if you connect a capacitor to a DC voltage, it will be open circuited. If you connect a an inductor to a DC voltage, it will be short circuited, right? So that's all about the summary of this chapter, right? So we'll see about some problems, right? Some tutorial problems in our next class, right? Meanwhile, if you have any questions, please send me, right? We have a WhatsApp group, just post your questions, right? Or take a photo and send it to me, right? If you feel bad to send your questions in front of your friends, just send it to me personally, right? I will go through it and get back to you, right? Any questions? If you have any questions? Right, if you have no questions, then we can wind up the session, right? Thank you. Any questions, please let me know. Otherwise, yeah, okay, we can wind up, right? You can go for your next class. Thank you.